Swayam Prabha. Digital India. Educated India.
Good afternoon everyone, welcome to the lab session again. So, I think you have got enough knowledge on what is PDP, how to do it, how to find E-core, I-core for a material. So, I think yesterday you have seen it for aluminum, right. So today we will see it how the bronze will perform in seawater solution and acidic rain solution. So, this is the bronze sample that we are going to use. So, already I have set up the setup and already OCP is running. So that we can move on to the PDP. Okay, can anybody tell why OCP we are running? Yeah, we will ensure the stability of the system. So, if the potential is stable, which means the system almost attained the equilibrium state with respect to the alkylate what we have inserted. So, there you can see that it is almost stable, it is almost running for 1 hour in the system you can see. So, then after that we will go on to the proceed for the PDP curve which is potential dynamic polarization. So, in here now I am using a NaCl solution. So, since it will take each experiment almost 2.5 hours, I have conducted already experiments and I will show you the results. This is just to show you how we are conducting. So, we all know that we are using a 3 electrode setup for potential dynamic polarization. Can anyone tell why we are using 3 electrodes, why not 2 electrodes? Okay, we are using reference, counter and our working electrode. Counter is to measure the current and the reference is to measure the voltage upon our sample. So, this is the typical curve, cathodic region, anodic region. The curve will be between the potential and log of current density. This is the theory behind TOEFL extrapolation. When we are doing a TOEFL extrapolation, we will find linear regions just above and below the E-core and E-core values, so that when you extrapolate that linear region, you will get the I-core value. So, that is our aim, to find out the I-core and E-core value for the bronze sample in acidic rain condition and in the seawater condition. So, as I have told you, I have conducted the experiments already in both the conditions. So, here you can see, can you all see, this red curve is in acidic rain solution and this black curve corresponds to the NaCl solution. So, from this, can anyone tell the inferences, like which is performing good, which is performing inferior? Yes, corroding more. Yeah. So, alkylate, it will contain carbonates, bicarbonates, nitrites and sulfate. So, it is like commercially available, we can also make it in our lab. Yeah. So, can anyone tell the pH of the acid rain solution and NaCl solution? NaCl is around 8 and acid rain, since it is acid, around 5 or 4.8 something. So, here you can clearly see that in the NaCl solution, like if you are going to, we will go to draw the tangents and we will determine E-core and I-core. Here you can clearly see that the performance of the bronze sample in NaCl solution is inferior, which means it is corroding faster, whereas in case of acid rain it is slower. So, it may depend on the corrosion, composition of the sample what we are using and the acid rain solution. And acid rain solution is not very what you call pakka composition, like it will vary with the regions and different regions of the world. So, there is nothing more to tell. We will draw the tangents, we will determine what is E-core and I-core in the both conditions, and we will conclude which is more corroding more. So, have you done determining E-core and I-core in the previous experiments? like aluminum for aluminum. Did they show you how to do it in the origin? No? Okay. So, according to the theory, yeah, in software I will, origin I will do.
You used to do it original.
Yeah.
That is more reliable than software.
Yeah, because that won't give, we are using to do this one. Yeah, it will give. Like, okay, sorry, it will give, but we are using this one because simultaneously we will plot the graph, we will take it, and equal ICOR also will simultaneously get it.
If we have, like, I have done PDP and it won't be like straight line, no? It will have so many
Very undulations.
fluctuations.
Okay.
So how will you do that?
So actually the thing is that undulations may come because of many factors, like surface if is not like smooth enough, or maybe alkalite, or sometimes because of the reference alkali also, if it is not stable. So
Curve will be like that only, fluctuations will be there.
okay,
So I want to determine like static slope for
that kind of samples. Okay, like generally that kind of ones we will do a, like there is a thumb rule where is from ECOR and ECOR value, if you go above 50 millivolts and below 50 millivolts, generally you will find the linear region for such kind of plots. So we will take it there.
from software only, we are using solar probe.
Okay.
We are using scripter associated software.
Okay.
Software I am getting, I don't know is correct or not.
Generally if it is around
that you are using scan rate, how much scan rate?
Scan rate for steel 0.1667 millivolt per second.
1667.
For that's the standard.
Okay. So I will show you how to do it in origin. So I have already plotted. Here you can see the y-axis potential and x-axis current density. So this current, can you tell what is this current?
What is?
This current, from where it is coming?
From that ions.
Yeah, like is it exact currents or difference of something? So it is a current difference of reduction reaction and anodic reaction. It is a difference of the both reactions. It's not of particular reaction. So why we are plotting log, and why like see like ECOR we can find very easily where that intersection point is there, but we can't find the ICOR directly. Why is it? Because the difference will be at the ECOR value, the difference will be 0. So at 0 if you apply log value, it will give negative infinity, which our potentiostat can't measure. So why we are plotting a linear regions, extrapolating them, so that at the intersection we will get the ICOR values. So first we will determine for the acid rain solution. So can you see these linear regions here? They won't be exactly linear.
So just drawing a line.
Yeah. So I am just showing roughly. While doing, we will do it more precisely. So this is how we will draw tangents, just 50 millivolts above the ECOR and 50 millivolts below the ECOR, so that the intersection will give us the ICOR value. So in origin there is an option called what is screen reader. So you can select that one and you will get a window like this. So, like it will be easy to find out the ECOR and ICOR values in the origin. So, you can directly go to that intersection point and you can click on it, it will give you the x and y values. So, the y value which is ECOR, it is 56 minus 56 millivolts, whereas the x value is like it will give in the log value, we have to apply anti-log to get the current density. So, can anyone apply and tell me the what is the I value? It is minus 5.934. Apply anti-log and just note down the value and note down this y value also. Note down.
I want to ask.
You remembered? Okay. Now we will do it for the NaCl solution. What is the ICOR value? Current density? Two. Okay, I'll do. It would be better every one of you are calculating. Okay. 2.7 milliamps. No, it will come microamps something. So, this one is 9.2 microamps per centimeter square. You have pen? So, in the acid rain solution, the current density value is 1.17 microamp per centimeter square, whereas in the case of NaCl solution, it is 9.2 microampere per centimeter square. So, from this you can tell that in the acid rain solution, the current density is lower, whereas in case of NaCl solution, it is more. You can attribute this to because of the fact that there is more chloride ion concentration. So, if you are doing in the very low concentration or ambient in any other alkalite, the chloride concentration won't be that much. So, depending on that, it is the one of the factors that decide the corrosion value. So, yeah, that's it. If you have any doubts, you can ask me.
Have you compared this pattern of manual computation of the ICOR value with that of the software? Have you compared the two methods?
I didn't understand.
Yeah, this process you use now, have you compared using the software to determine the ICOR values? And
With
the
software?
yeah.
Yeah.
Have you
Like
compared the two?
they are like almost near. Since it is manual, there will be some errors.
Why can't you think that maybe the software is better than this method? Using the software, you give more accurate result than this.
I didn't understand.
You using software is more reliable than this instrument.
No. Like software, she told she is getting some undulations there. That time software won't detect.
It will give some values, but we can't tell it's correct or
Yeah,
not.
like it's like
Depends on how you.
Which software are you using?
I'm using from Scrivener Associate.
No, you go and use
No, better. The software only will support my machine.
no, you can use Ikem to check it. E-Ken software for fitting.
both side is not needed. Only one side is enough. Yeah, one side is enough. They should not differ theoretically, but it will differ.
Deciding the linear region in the anode side is somewhat difficult comparing to cathode.
Yeah,
The linear regions we may identify 2-3 spots.
yeah.
So how can we?
So that time we have to see here the linear region. If it is in the at least 1 decade, it should be linear. So here 1 decade means in the log plot. Yeah. So if it is 1 decade minimum, it is linear, then it will be fine. -5 to -4 or -4 to -6 like that. Then we can be sure that it is like accurate enough. The more linear it is, the more accurate. Like 2-3 spots exceeding. Oh, generally we'll take the one which is closest to the E core. Yeah. And also sometimes you will get different like multiple loops. It is just only one loop, right? You will get different loops. Like that time you will get like multiple E core and I cores. That time we will take which is the lower one, because that's where the metal is starting to corrode first. The above all, like sometimes they will correspond to the passive layer or some other reactions.
Can we find exchange current density?
Exchange current density. This is what exchange current density.
The ICO, right? Exchange current density means it's in equilibrium.
Equilibrium. Yeah, this is what in equilibrium, right? If you put the metal in the alkalite, it is getting corroded.
But it is reversible.
No, you are talking about, you are confusing. This is a corroding system. That is single electrode system, which is not corroding, like AgAgCl. It's not corroding.
So if any metal I am taking and I need their exchange current density, then ICO value.
Yeah. So it matters whether it is corroding or not.
And did you do like oxygen reduction and hydrogen evolution? I need to find their exchange current density.
That I didn't do.
No one did.
I don't know. I didn't do. Generally, we will change it every time. Yeah, we will change it each sample, because the dissolution will happen, and the two like the time which we are exposing alkaloid to the environment, the oxygen dissolution may increase. So definitely it will create some problem.
Is there is any theoretical formula to calculate ICO?
Theoretical formula. I don't think there is a theoretical formula, but there is a formula that tells that there will be linear regions. So using that linear region, we are plotting, extrapolating, and we are finding it out. I don't think there is a formula to directly find out I core.
No, using those values, using the current.
If you are getting current, what else we need? That's all current values. I don't think so. Generally, we will find the slopes only, not the I core value. See, porosity or surface roughness. So suppose like what here I am exposing is around 11 mm dia of circle. So if it is very smooth, the area which I am exposing will be exactly matching to that circle. So, if there is porosity, which means the material is not there, or some surface roughness, which means it will have some ups and downs, in that case definitely the surface area will differ. So, it will be high. So, in case of porosity it will be low. So, then the potential will not change E core and I core, but the current density will change. Current will change, not the current density, but you need to know the exact area to determine the current density. Current density should be exactly same. So, why we will polish it minimum till 1500 silicon carbide paper to get a very smooth finish. Generally it won't. Yeah, I core won't change. Like the current will change depending on the area which we are exposing, but I core won't change. I core is a current density, it is not just value.
So the remaining area you won't use for any,
Not like that. Like the remaining area will tell how the material is behaving at different potentials. Say suppose I am doing corrosion studies for bipolar plates. Yeah, in that case, so can you see that two potentiodynamic curves there in that poster? You can see the I think left side one is cathodic condition, which I will purge the oxygen. The right side one is anodic condition, which I will purge the nitrogen to simulate anodic and cathodic conditions.
you will nitrogen what you will do?
Purging through the alkalyte to remove to deaerate the solution. So, there you can see in case of cathodic conditions the operating voltage is 0.6 volts. In case of anodic condition it is minus 0.1, but my E core and I core does not matter that much. What I will look in that situation is that okay. See here I will generally find out E core and I core, but in case of cathodic environment my point of interest will be here. I will draw a line, I will see how it is behaving. At that voltage what is the passive current density, or whether the material is in active region, whether it is passive, like that I can find out.
Where it is used in this bipolar?
In fuel cells. Potential generally alkalyte will affect definitely, because the reactions, basically the reactions what are happening, that will affect the potential. So, it is the alkalyte and the material and what is there at the interface. Yeah. That you are asking about the reference electrode. So, we will generally change it according to usage, maybe 1 month, like that. If you are using too frequently, yeah, quite often you need to ensure that it is calibrated.
You are using AJs.
Yeah.
You will change means you will use the new one after 1 month.
No, I will just dismantle it, I will remove the KCl solution, I will fill it again and I will calibrate.
Calibrate using the new reference electrode, and how you will calibrate?
With respect to another one.
Another reference.
Yeah. If I am using another AGACL, the difference should give almost near to 0.
You are using saturated thermal.
Yeah, that also we will use.
Writing for it, we cannot do much using this.
Which one?
Current is high, current is high, the corrosion rate is high, and that's something we can discuss. Other mechanics
From this PDP. No, not like that. See here, this curve here, it is not perfectly it's not perfectly linear. So, this one can correspond to some other reactions, whatever there is present in the acid rain. See, for acid rain only it is kind of more undulations, which you can tell that at that particular voltage there may be some dominating reactions, there may not be some. like acid rain contains generally this carbonates, bicarbonates. At that potential something may react, something may not be active. So, everything you can find out as a collectively, but not like separately. So, yeah.
Between PDP and the impedance, which one is more correct to check efficiency, to predict efficiency? Between this polarization and the impedance, which one is best to predict?
Best means each one have its advantages. We can't tell like that. It is a DC measurement technique which is destructive one. So, we are polarizing the material with like from the equilibrium. So, it will dissolve the ions, whereas EAS it is not a destructive method. It is just AC measurement. We will apply certain frequency of AC current and it will give you the response. So, from the EAS you can tell that resistance value. Based on the resistance you can tell how corrosive it is, but it is not very direct. Sometimes it may differ because of the surface. It is more surface sensitive.
When the PDP itself is closely varying, whether the same current can be observed in this one EAS?
No. It will gives you the that resistance value only. So, this precisely we can't. Here we can control the scan rate. So, now I am using 10 millivolts. If you need more precisely, you can reduce the scan rate
10 millivolt
per second. Point 010 millivolts per second. 010.
Usually for the metal form, for 1667 like millivolt per second, right?
Which one?
Usually for metals in solution, you would use the scan rate 0.1667.
It don't have to be that value only, but we should maintain a constant value.
I also have here that 0.166 many places. I
If
don't
you
see why that
increase the
is.
point,
It depends on what we are drawing, like how much accurate information you need. See, suppose like 10 millivolts, like at 10 millivolts some reaction is happening, at 15 millivolts something may happen, but at 15 millivolts I am not measuring the current, I am measuring it again 20 millivolts. So, if you need more precise data, the steps should be vary. That is so precise. It varies with the application. So, in case of biomedical materials, we will use very small step rate. So, we want to get a very accurate data. Here we do not have to use that.
How can we characterize the products?
Corrosion products. So, if they are dissolving, you can like characterize the alkylate, what ions dissolve before and after, and if there is some product forming and it is adherent to the material, you can characterize with XRD, SEM.
did you do any modeling for
No one is doing modeling here. So, anything?
What are the types of corrosion we can observe in this?
Types of corrosion. Yeah, uniform corrosion, like generally this one. Pitting you can observe from the upper portion of the PD curve. So, that pitting generally it comes under this active passive materials. There you can see when the passive layer is breaking down. So, we will use a repassivation technique to find out what is the susceptibility also. Okay, if you are done, I will just introduce my work, what I am doing, if you are interested. So, generally I am using a high, do you know anyone plasma alkylating process? Okay, like plasma alkylating process, it's like there is alkylate and plasma also will form on the surface. We will use very high voltages, minimum of 200 volts like that, so that when you are applying high voltages in between the working surface and the counter electrode, there is a formation of plasma on the surface. So, at that plasma, because of that plasma, there is a formation of very high temperature only in the localized region. So, since it is the sample is in the alkylate, the ions from the alkylate will move into the surface and they will modify the surface. So, it is a like surface engineering technique, you can call it coating, but it is not exactly coating, it is a diffusion coating. So, like that you can modify the surface, can increase corrosion properties, wear resistance and other tribological properties. So, that is what my work is. I will do it for metallic bipolar plates and I will test it in the fuel cell conditions.
Usually what do you use in fuel cell?
Generally people are now using graphite only. Yeah.
What is it fuel?
It is very brittle and very heavy. Yeah. High temperature it can withstand, but FEM fuel cell they won't go beyond 90 degrees centigrade. So, temperature is not a issue. So, it is very brittle and because of that it will be very bulky. We can't use it for the automobile applications. So, people are looking for the alternative materials like metals, and we have to groove the flow channels to send the fuel like oxygen or hydrogen. So, for that we need to groove the like flow channels.
Flow channels.
Yeah. So, these grooves are known as flow channels. There will be different types in that. So, grooving on a graphite is very difficult and very expensive, and also since it is brittle, like it may crack if you are not taking care, but in case of metal we can stamp it, and also we can use very thin sheets of bipolar plates. So, but the problem with metallic bipolar plate is corrosion. So, that is what we are studying.
On which solution you are doing?
So, generally I am using aqueous alkylates only, one is urea based, another one is acetic acid based.